Assalamu alaikum, dear students. Today our topic of discussion is going to be design of beams. In the previous lecture we had gone through analysis of beams where we looked into three cases. The first one is laterally supported beam, and then we had a laterally supported beam with cover plates and laterally unsupported beam or a discretely supported beam. So today's discussion is going to be regarding laterally supported beams, then we'll have laterally unsupported beam, and again laterally unsupported beam. We'll be dealing with the design of these beams. Now the first question is design of laterally supported beam. Now, as we discussed before, a laterally supported beam is a beam which is supported laterally throughout continuously. So if we have a member like an I-beam, when we say it is laterally supported, we mean that along this direction it is laterally supported throughout. So the idea is you really try to prevent lateral buckling. So that means you need not check lateral torsional buckling, because your member will not fail by lateral torsional buckling. So you have to only worry about local buckling. Even in design, your approach, your choice of section is going to be purely based on local buckling. So this question says we need to select. From the word select, it is clear that it is a design problem. Select the lightest W shape for a laterally supported beam to carry the concentrated load, which is 50 kPa, and uniformly distributed load, that is 10 kp/ft, both are service loads. The self weight is included in the uniformly distributed load. Use Fy is equal to 60 ksi steel. Check for deflection, given the maximum allowable deflection is L/360, and check concentrated loads. And you will also have to check for shear, which is understood. Now, based on the service loads given, we can find the ultimate loads. P ultimate is 50 times 1.6, that is 80 kPa. Wu is 10 times 1.2 is 12 kp/ft. Now the next step is to find the maximum moment and maximum shear for this beam. Now this is similar to the analysis problem. We use structural analysis to find the maximum moment and shear. These are the ultimate loads. Based on the ultimate loads, we find the reaction Ra from equilibrium is 112 kPa and Rb is 256 kPa. Based on this, we construct the shear force diagram. To construct the shear force diagram, we start off from the left end. We have 112 upwards, so we go up, and then because of the distributed load, we have an inclined line, that is 112 minus 12 times 8, you reach 16, and because of this concentrated load it drops to minus 64. Then again 12 times minus 64 minus 12 times 8, you get minus 160, plus the reaction Rb 256, you reach 96, and then when you subtract this again, you would reach to 0. You should reach to 0. Now once you have found the reaction, you can develop the equation for bending moment for this region. For this region you can develop the bending moment equation as mx is 112 clockwise moment minus 12 times x squared by 2. And based on this, you can find the maximum moment, which is 512 kPa, and on the other support we can find the moment using W, this moment 12 times 8 into 8/2, you get minus 384. So from these two diagrams, it is clear that the maximum shear force is 160 kip and your maximum bending moment is 512 kip feet. So these are the design moment and design shear force that we use. Now the next step is to get the section. Now for that, the assumption is that the section is compact. So assuming that the section is compact, we can use equation F2.1 to estimate the Zx value. So this means that you assume, when you say it is compact, we assume that the section fails because of yielding. So we can directly use phi mp, phi mn is equal to phi mp is equal to phi fy zx greater than or equal to mu max. This can be taken from the manual. From the manual, it is clear. It is available over here on page 16.147. This is because of yielding. So based on that equation, you can find Zx is mu over phi fy is equal to 512 times 12 to convert it into kip inch, divided by 0.9 times 60 because the fy value is 60 ksi. So the Zx required is 113.78 inch cube. Now we need to get the section from table 3.2 or the Zx tables that we discussed in the earlier lecture. So if you take the Zx table as I've marked here, this is the Zx table, and the value of Zx required, we have to enter this table with 3.2, table 3.2 with Zx is equal to 113. So if you observe, the Zx values are very high here. We need to go down until we reach 113. You see 113 is right over here. But as we discussed, this is a group, and the section in bold is the lightest section. So we need to take W21 by 55. So we try W21 by 55 with Zx is equal to 126 inch cube. Now once we have chosen this, we have to check the local buckling, and for checking local buckling you have BF over 2TF is equal to now before we proceed, we are checking this because our Fy is 60 ksi. If it was 50 ksi, we could have ended it right here. We don't have to check local buckling because this table that we just referred is based on Fy is equal to 50 ksi. So the value that you get is the final value. But since we are dealing with 60 ksi, we need to do this extra step to make sure that your section is compact. BF by 2TF 7.87, which is available from the dimensions table, and then H over TW is 50, which 2 is available from the dimensions table, and you need to check it against local buckling of the elements. So that is available from table B 4.1b, which is flanges of rolled I shape 0.38 square root of E over Fy and 3.76 square root of E over Fy. This is for H over TW. And once we have made sure that it is compact, we can assume, we can be sure that the section is going to fail by yielding. And therefore, the moment capacity phi mn is equal to phi mp is equal to phi fy zx. 0.9 times 60 times zx. This is the zx value of W21 by 55. So you get a value of 567 kip feet, which is greater than mu max, which is equal to 512 kip feet. Now the section is sufficient for flexure. Now you need to check for shear. To check for shear, again we go into table 3.2, which lists the value of phi Vn for different sections. So if you take go to table 3.2, but the table has listed the value of phi Vn for 50 ksi. So to find the phi Vn value corresponding to 60 ksi, we need to use this technique and cross multiply. So the unknown, so for 50 ksi is 234, for 60 ksi is equal to phi Vn prime. So phi Vn prime is calculated by cross multiplying these, and the value is 280.8 k, which is definitely higher than the maximum shear that we got from the structural analysis. Now the next section is to check concentrated loads, and from the figure we have 3 concentrated loads. We have the applied load and we have the 2 reaction, where this and this is interior concentrated loads, and this is an exterior concentrated load. Now both of these equations are available in section 16.1, page 34. Now let's consider the first interior load. We have LB as the unknown. We solve for LB, and when we solve for LB while using all these values, it'll be nice, it'll be easy if you could just list these properties along your solution, so that you can quickly fill in these values, because they come in handy along the way. So LB value is greater than minus 1.54, which means you do not need a bearing plate there because of web local yielding. Now to check for web local crippling, we have the equation from the manual. Find the value of LB. Bearing plate is not required. So for this particular interior load, you don't need a bearing plate. Now we repeat it again with the second interior load, which is RB is equal to 256 kip. We check it for web local yielding and web local crippling, and we get 2 values. One is 6.28, the other is 10.81. So we can take the largest and then round it off to the next whole number, which means LB is 11 inches. So we do need a bearing plate there. Now the next section, now the next concentrated load that we need to check is RA equals 112 kips. And when you check the web local yielding, because of this load, we get a value of LB as 2.42. And again, for web local crippling, you have to check these both criteria, and your LB value is 8 when you check this criterion, and when you check this criterion, LB over D is greater than 0.2, you get LB as 7 inch. You take the larger of the two and round it off to the next whole number, so you get 9, and then you can draw a small figure to show the value, the length of bearing plates that you have used. So in this support we have 9 inches, and in this support we have 11 inches. To check for deflection, we have to always use service loads, because deflection is a serviceability limit state of serviceability. So your P value is 50 and your W value is 12 kip per feet, and this deflection values are available from the manual. Now let's see how these values can be used. Now if you take this section, this is case 24. So our problem can be split into 2 cases. Our problem can be split into 2 cases because we have distributed load and a concentrated load. So you can this split it into one beam with uniform load and another beam with a concentrated load. Now this corresponds to case 24 from the manual in tables 323, while this corresponds to case 28. So the idea is we need to find deflection at 2 points. One is at this point because we expect this to bend like this. So we have one deflection over here. Let's say that this deflection is delta 1 dash and this deflection is delta 2 dash. And for this again we expect this to bend like this and then go like this. So we have one deflection here as delta 2 dash right below the distributed concentrated load, and you have another deflection delta 1 double dash and delta 2 double dash. So from case 4 you find the two required deflection. One is delta 1 dash right in delta 1 dash over here, and this is calculated using this deflection is calculated using this equation which is available in case 24. Now for concentrated load, which is case 28, as we discussed, we need to find two deflections. One is this deflection, the other one is this deflection. So this can be found from the manual, and then we need, so the midspan deflection is sigma 1 dash plus sigma 1 double dash, which is equal to 0.464 inch, and for the overhang it is delta 2 dash plus delta 2 double dash, which is equal to 0.067 inches. Now the limit of deflection which is given to us is L over 360. When you calculate L over 360, you have 16 times 12 divided by 360 is equal to 0.53 inches greater than 0.334, which means our deflection is less than the limit. So the design is complete here. Now the second problem is design of laterally unsupported beam. We have two problems in the design of laterally unsupported beam. The first one is relatively very easy compared to the second one, and I'll tell you the reason why. Select the lightest W section for the beam shown below. The concentrated load consists of 5 kip dead load and 15 kips of live load. Lateral supports are provided at supports and concentrated loads, which I have not shown. So the ultimate load can be found by applying the factors, load factors 1.2 dead load plus 1.6 live load, which is 30 kips. Now based on this, since we have found WU from the symmetric loading condition, you can predict that the reaction, you can find that the reaction is WU here as well. So your shear force diagram will look something like this, because we have WU, it is constant, then you have WU, and then you have some region of zero shear force, and then you have WU constant shear force, and then 0. And when you draw the bending moment diagram, you see that you have this region of constant bending moment. So if you go ahead, we need to determine the critical segment. We go ahead. Now we have two segments here. We have three segments: segment 1, segment 2, and segment 3. And it is very clear that segment 1 and segment 3 is identical, is similar because of its symmetry, while segment 2 is another case. So you have to split it into these segments as shown. AB or CD LB value is 10, M0 M1 is the smaller moment and M2 is the larger moment. So in this region, in this segment, 0 and minus 300, so 0 and 300, and the CB value can be calculated as 1.75. Let me show you how. CB value can be calculated using this equation. CB is equal to 1.75 plus 1.05 M1 over M2 plus 0.3 M1 over M2, this whole square. This is available in the manual in the commentary section in page 16.1304. CB is over here for linear bending moment diagram, and for non-linear bending moment diagram we have CB from here. So you get a CB value of 1.75 and you get an LB over CB value of 5.71. Now the next segment is BC. The length of BC is 30 feet and M1 and M2 both are 300 because the maximum and the minimum value is both the same, and the CB value is 1 because if you substitute the value of M1 M2 in this equation, we get the value of 1. Now the idea of CB is to be discussed here. We discussed in the class, you had already learned in the lecture, but CB is like a ratio representing how much part of your beam, if your segment is actually utilized. For example, if you consider this segment, which is between these supports, you see that the entire segment is loaded with the same moment, which means that your entire beam is taking the maximum bending moment. While if you take another segment like this one, here it is 0 and here it is 300. So only the usage of, the utilization of the section for carrying the bending moment is actually varying. It is varying from 0 to 300. So therefore you use this equation to calculate this one. So when it is 1, it means that your entire beam is utilized. So anything above 1 means it is not completely utilized. So you can find the value of LB as LB over CB from this equation. Now if you just take a look, when we go ahead, we have CB is equal to 1, mu max is equal to 300, because this section controls, because it has the maximum moment as well as the maximum LB over CB, and your Fy is equal to 50 KSI. Now if you go into the charts table 310, there is something that we need to notice here. The Fy value is 50 KSI and CB is equal to 1. So this chart, all of this chart corresponds to Fy is equal to 50 KSI and CB is equal to 1. Now this problem that we are doing right now, we have Fy is equal to 50 KSI and we got our critical segment having CB is equal to 1. So we can directly choose a section and we did not check it for LB, local buckling and lateral torsional buckling. So we have our moment as maximum moment is 300 and our maximum and our unbraced length as 30. So when we go ahead, the value of Vmn is very high here, so we have to go to around 300. So when we reach page 3-125, we have the value of 300 over here and the value of unsupported unbraced length 30 over here. So when we match this along 30, we reach this point. To select the lightest member, we need to go diagonally. So when we go diagonally, we come across W14 74, W16 7/77, W18 by 76, and so on. So the most economic section is corresponds to the line which is solid. That is, W14 by 74 is a solid line, while W16 by 77 is a dotted line. So the nearest economic section is going to be W14 by 74, and we don't have any dotted lines in between. So this is our first and the best choice. So W14 by 74. So the section can be chosen from table 310 without checking local buckling as well as lateral torsional buckling. Okay. Therefore, we can choose W14 by 74. Local buckling and lateral torsional buckling need not be checked because it is okay, because the charts have been derived for this condition, which is CB is equal to 1 and FY is equal to 50 KSI. Now I have drawn a simple diagram here just as a general procedure to show you that your MU max, you have LB over CB, and the nearest solid line diagonally is the first choice. Now we have to check the shear capacity. Your VVN is available from table 3.2, which is greater than your maximum shear, which is 30 kip. Now the next step is checking concentrated loads, and in the figure we have the problem. We have 1, 2, 3, 4 concentrated loads. 2 are exterior, and 2 are interior. Owing from symmetry, and you know the values, they are the same, so you just need to analyze this and this. The interior concentrated load is the reaction, which equals 30 kips. You check web local yielding, you check web local crippling. You find that both of them do not require a bearing plate. Again, we check concentrated loads, the external ones, which is equal to 30 kip again. So we have web local crippling, web local yielding, and web local crippling, and then we get the LB values as negative, which means we do not require a bearing plate. So this is the end of the second problem. The third problem is a laterally unsupported beam, but with some differences compared to the second problem. For example, we have 60 KSI steel, and we see that the segment CB values are not equal to 1. So the problem is to select the lightest W shape for the beam shown in the figure below. The beam is simply supported and has lateral braces as shown in the figure. We have 1, 2, 3, 4 lateral braces. And the W dead load and W live load have been given here. So your WU is 1.2 W dead load plus 1.6 W live load. You get the ultimate distributed load, and then from that you can find the ultimate moment, and also the shear can be calculated, which is 32.9 from structural analysis. Your maximum moment, which is at this point, is 287.88 kip feet, and your shear force is 32.9 kips. Now the next section is to determine the critical segment. Now we know that determine the critical segment involves the calculation of CB. Now we have three segments here. We have AB, BC and CD. AB and CD are identical, so we just have to deal with AB and BC. Now segment 1 and 2, which is segment AB and CD, the CB value is calculated using this equation because it is a non-linear bending moment diagram. So the value of moments MA, MB, MC and Mmax is calculated from the bending moment equation, and these are the distances. First of all, you have to have 4 equally spaced parts, so 15/4, 15/4, 15/4 and 15/4. You substitute the values of distance as we develop the bending moment diagram. Substitute the values of MA, MB, MC and Mmax and substitute these values inside the CB equation to get the value of CB. Again, we repeat the procedure for segment C, segment BC. In segment BC, we see that your MA and MC is going to be the same because of the symmetry, and your MB is equal to Mmax, which is 287.88 kip feet. When you substitute these values inside the CB equation, you get the value of CB as 1.002. Now we can make the table to find the values of MU max as well as LB over CB. So segment ABCD, you have 15 feet LB, your MU max is 282, CB is 1.375. You can find the LB over CB as 10.91, and your BC has an LB of 5 feet and your MU max as 287.88, your CB as 1.002 and your LB over CB as 4.99. Now straight away we can guess the most critical, straight away in the sense we have AB over CB as having the maximum LB over CB and segment BC having the higher moment value. So if any of the segment had maximum value of MU as well as LB over CB, suppose we had BC with the maximum value of MU max and the maximum value of LB over CB, we could have directly taken that section. But in this case, we are in a we cannot directly decide because one segment has the higher MU max while the other has the higher LB over CB value. Now in this case, what we do is we choose one section and check for the other, which means we choose section ABCD based on a judgment. For example, in this case, we see that even though the moment is small, it is only slightly smaller than this one, and your LB over CB is much higher. So it will be a better guess if you could have started by choosing this segment and then checking the capacity on the other. We'll see how. But as a general procedure, suppose you are in a position that you cannot really decide based on these numbers, you can do this procedure. That is, we find your Fy value 60 ksi, your Mu dash can be found. First we consider this segment. Your Mu dash can be found by 282 times 50 over 60, which is 235. You have to enter table 310 with 235 and LB over CB is 10.91. So if you take into the manual your value is 235, which is somewhere over here, and your LB over CB is 11. So it is almost over here, which means the nearest solid line is 21 by 44. That is around 235 is over here, and your 11 is over here, and the section that the solid line that you see the nearest is W21 by 44. So this is one of the trial section that we can start with. Now you can estimate a section for segment BC. You have 287 and LB or CB as 4.99. So since our FY is 60 ksi, you have to convert it into equivalent value. So you have 287 into 50 divided by 60, which gives 239 kip feet, and your LB over CB is 4.99. So we enter the table. So we go into 240, which is almost over here, and your LB over CB value is almost 5. So the nearest section that you see is W18 by 35. So when you compare these, we see that W18 by 35 is the lighter section. So you can begin by trying this section. So as soon as you start off, we have to check the local buckling. We find the local buckling and we see that the section is compact, and you can determine the value of phi MP 0.9 FYZX, which is equal to 299.25 kip feet, which is higher than your maximum moment. And then you can check lateral torsional buckling. To check lateral torsional buckling, you need two values. One is LP and one is LR. Your LP is calculated from 1.76 RY square root of E over FY, and your LR can be calculated from this equation. And LP and LR, as we discussed, is taken from chapter page 16.1, page 48, where LP and LR is listed here. The constants can be taken from the manual, and then you get the value of LP and LR. Now once you have found this, you have to check the capacity from lateral torsional buckling for both the segments. So the first segment and the third segment, which is identical, your LB value is 15 feet. So your LP, LR, LP is less than LR, which is less than LB, and the value of phi MN is calculated from phi FCR SX, which is available in the manual. In this section, equation F23, because in lateral torsional buckling, we see that you have when LB is less than LP, which means lateral torsional buckling does not apply, which means it fails by yielding. LP less than LB less than LR, we have this equation, and then when LB is greater than LR, we have this equation. In this particular problem, we have to use this case because the LB value is greater than LR, and in this there is a value called FCR, which is calculated from this equation, and all these values are available in the manual, and therefore we get FCR is 34.62 ksi, and your phi MN can be calculated as 0.9. This is FCR and this is SX. You get the value as 149.55 ksi, which is less than mu max. So therefore this segment cannot be used. See, your maximum, the maximum moment in this segment is 282, and what you have got is just 149. So this cannot be used. Hence we have the next trial section, which is W21 by 44. Again, check local buckling, get the value of phi MP, and then we check lateral torsional buckling. To check lateral torsional buckling, as we discussed, we need to find two constants, which is LP and LR. LP is found from this equation and LR is found from this equation. And again, you see that the LB value, which is 15 feet, is less than, is greater than LP and LR. So we have to move into this equation. Phi Mn is equal to phi FCR Sx, as we discussed earlier. We get the value of FCR as 37 and the value of phi Mn as 229.86, which is slightly less than mu dash. So there is a slight correction here, which I will correct in the notes, that it is mu is 287.88. It is not mu dash here, as I just told. Now it is mu is less than the phi Mn is less than mu. So which means that this section is again not sufficient. So we have to find the next larger section, which is close to W21/44. So if you take the manual, we have to enter the manual with these values as we entered earlier, and then find the next solid section after W21/44. So when you open the manual and check it out, you find that W16/45 is the nearest section. So now check local buckling, find phi MP. You see that this value is greater than mu max, and then check lateral torsional buckling. To check lateral torsional buckling, we need to find LP and LR. Your LP value is 5.0706 feet and your LR value is 14.65 feet. Now you have to check this against both the segments. You have segment 1 and 3, or AB, CD. So the LB value is 15. Your LP, LR, LB value, you see that your LP is less than LR, which is less than LB. So again, you have to use this equation. For that, you need to find the value of FCR, which you calculate to get 55.57 KSI. And when you substitute phi Mn, we get the value of phi Mn as 302.99 kip feet, which is higher than 287.88 kip feet. So which means the section is sufficient in segment 1, 3. Now we need to check the same section in segment 2. In segment 2, we have LB is 5 feet. You have LB is less than LP less than LR. Therefore, your phi Mn will, which means that your section will not fail from lateral torsional buckling. It's got to fail by yielding. Your phi Mn is equal to phi FYZX, which can be calculated as 370.35 kip feet, which is less than mu max. So mu max of that segment, which is 282. Which is 287.88. So once we have found the value of LP and LR, we need to check the capacity in both the segments. So segment 1, 3, which is segment AB and CD, the LB value is 15. Therefore, when you compare with these, you have your LP, which is the least, and then you have LR, and then you have LB. Therefore, the equation that you choose to find the capacity is phi Mn is equal to phi S FR Sx. Your phi FR or phi F critical can be found to be 55.5 Sin KSI, and your phi Mn can be calculated as 302.99 kip feet, which is greater than the maximum moment in that segment, which is 282. The second segment, the LB value is 5 feet. Your LB is less than LP less than LR. your phi mn is phi fyzx, because the section will not fail from lateral torsional buckling. It's going to fail from yielding. So you get the value as 370.35 kip feet, which is higher than the mu max of that segment, which is 287.88 kip feet. Therefore your section is safe and it is the most economical. Now we need to check the shear capacity. Your VU max from structural analysis is 32.9 kips. Here from table 3.2 or the ZX tables, you can find the value of VVN for 50 ksi. Therefore for 60 ksi you can cross multiply and find the value of VVN prime as 167 into 60 over 50, which is 200 kips, which is greater than VU max, which is equal to 32.9. Hence you can choose W16/45 as the final section. This is the end of design. Also in the problem we are neglecting checks for deflection as well as concentrated loads. If it is asked, you need to find and you know the procedure from previous problems. Thank you.